Let us quickly go through a few very important concepts in the theory of differential equations. Right? So algebraic equation is not an ordinary differential equation, because in algebraic equation an unknown is a scalar, so is a real number, maybe a complex number, whatever. So in a functional equation, the unknown is a function. So just like in an ordinary differential equation, the unknown is a function, but there is no derivative involved. So it's just the functional equation. It relates the values of the unknown function at different points. So then an ordinary differential equation, it relates an unknown function and its derivatives evaluated at the same point, right? So here are a few examples. So unknown function v, unknown function f. So here second derivative appears. Well, here we have the second derivative of the unknown function and we take its cosine, but still we have an unknown function. We evaluate it at itself, and it's its first derivative, its second derivative, we take the cosine and whatever. It is still an ordinary differential equation, right? So let's just for convenience use t for the independent variable and y of t for the unknown function. So then let me maybe once again write it down. It's very important that an ordinary differential equation, it involves the following. It involves the independent variable t, the unknown function evaluated at the point t, the first derivative of the unknown function evaluated at the point t, the second derivative of the unknown function evaluated at the point t, and so on. It is very important that they are all evaluated at the point t. So this is what the word ordinary is about. So the word ordinary means that there is just one independent variable, and our differential equation, it involves the values of the unknown function evaluated at t. So for example, if say, because you could imagine something like maybe imagine that you have y prime, but y prime is evaluated not at t but at t plus 1, and then this is the same as say y of t plus t. You could try to find functions, unknown functions y of t, such that if you take y prime evaluated at t plus 1, then you get the same expression as if you take t and plus y evaluated at t, right? So this is a differential equation, but it is not ordinary. So this is called a delayed differential equation or a functional differential equation. Well, then a solution of an ordinary differential equation is just any formula that if you substitute it to the differential equation, then you get a correct equality. So here is an example. So this is an ordinary differential equation. So here is a solution, and it's very easy to verify. So you just need to find, for this particular formula, you need to find dy dt, and you need to take y multiplied by minus t over 4. So one is left-hand side, the other is right-hand side, and you see that they're exactly the same. But then, of course, you can try multiplying these by different numbers, and you will see that they're also solutions. Well, and then it is important to distinguish between the noun solution. So solution is any particular formula, right? So for example, this differential equation, it has different solutions. So one that we verified before is e to the minus t square over 8. But 25 times minus t square over 8 is also a solution, right? If you multiply it by minus 2014, then you also get, I don't know, say y equals 0 is also a solution, right? Because the derivative of 0 is 0, and then minus t over 4 times 0 is 0. So then is also a solution. Well, so this differential equation has a lot of infinitely many solutions. And, well, you may guess that all solutions are given by this formula, that is just a constant times e to the minus t squared over 8. And it is true, but it is a bit difficult to prove that there is nothing else. So that's the topic of the next lecture. It is true, but we are going to do it the next time. So then the order of an ordinary differential equation is just the highest order of derivatives involved, right? So if our equation only has the first derivative and no second derivative, no third derivative, and so on, then it's a first order ordinary differential equation. All right, so here is a second order differential equation because it involves y double prime, no matter that it is cubed. So it's okay. So as long as it involves y double prime but does not involve y triple prime, well, fourth derivative, fifth derivative, and so on, it is a second order. Right? Maybe I just need to mention that this notation means, well, when we have a superscript in round parentheses, that's the 2017 derivative. So we take the unknown function y and differentiate it 2017 times. Right? So that's an ODE of order 2017. Well, and then usually an ordinary differential equation, it doesn't have to be, but usually it can be easily written in the form where the left-hand side is the highest derivative that appears, and the right-hand side is everything else. Right? So, for example, I don't know. This one we can rewrite as y double prime equals 1/3 y prime minus 1/2 y. So we just move everything to the right-hand side. Right? So this we can rewrite as y double prime. We move everything to the right and divide by 6. So 1/6 2y prime minus 3y. So the left-hand side is the highest derivative, and the right-hand side is everything else. Or it can be easily rewritten. So if it cannot be easily rewritten in this form, then it is still an ordinary differential equation, but it is sort of a bad one in the sense that there doesn't exist a general theory for these equations. So all the theory of ordinary differential equations, it refers to differential equations where the left-hand side is just the highest order derivative involved, and the right-hand side is everything else. The reason for it is, well, you will see it in week 4. It is because we have the theorem of existence and uniqueness of solutions. Okay, now finally, I suggest that you, instead of watching the lecture, you just go to this link and you try to take a little recap quiz about differential equations. So this is how it looks like. Allow. Let me see if it's going to work. Yeah, okay, excellent. So that's the quiz.